Welcome to this video that goes ahead and explains all of our flow chart that we've learned for mean arterial blood pressure. This is subdivided into cardiac output and total peripheral resistance. Remember, cardiac output is just affecting the heart, and total peripheral resistance is affecting mainly the arteries. And these, both cardiac output and total peripheral resistance, contribute to blood pressure. So if cardiac output increases, blood pressure increases. If total peripheral resistance increases or decreases, blood pressure also decreases. Okay, so what we're going to do is we're going to explain how cardiac output is affected by heart rate and stroke volume. And all of these everything that affects heart rate is going to go in this box. Everything that affects end diastolic volume will go in this box. Everything that affects end systolic volume will go in this box. And total peripheral resistance is affected by three things. Okay, so let's go ahead and get started and delete all of that. All right, so first things first, we're going to do cardiac output and we're going to do heart rate. So heart rate is directly going to be affecting the SA node of the heart. And we can stimulate the SA node via the medulla oblongata, right? And the medulla oblongata has two centers. We have the acceleratory center and the I'm going to put that a little further down. Inhibitory center. Okay. The cardioacceleratory center is mainly going to be sympathetics, so sympathetic nervous system, and inhibitory center is going to be parasympathetic nervous system. Awesome. So sympathetics are going to be delivered to the SA node via the sympathetic chain. And parasympathetics are going to be delivered to the SA node via the cranial nerve 10 vagus. Awesome. So now we can think about what happens if we increase sympathetic nervous system. If we increase sympathetic nervous system, what is that going to do to heart rate? Well, that'll increase heart rate. And if we're increasing heart rate, that will increase cardiac output. If we increase parasympathetics, parasympathetics will decrease heart rate, and that will decrease cardiac output. Awesome. All right, so that's it for medulla oblongata. I'm going to go ahead and erase all of this and continue on to the two other items that affect heart rate. Okay, so the next thing that we have to think about is venous return. And venous return is the amount of blood that comes back into the right atrium. Okay? And venous return, we can either increase venous return, and if we increase the amount of blood that comes into the right atrium, well, then the heart is going to think we need to contract more often so that we can move that blood efficiently, so that'll increase heart rate, which will in turn increase cardiac output. If we decrease the amount of venous return, that will decrease heart rate and thus decrease cardiac output. All right. The last thing we have to think about for affecting heart rate are hormones. And the hormones we like to think about are epinephrine, norepinephrine, and T3, T4. Well, T3 is our active form of thyroid hormone, so I'll leave it as T3. And collectively, if we increase the production of these hormones, that will also increase heart rate, which will increase cardiac output. If we decrease these hormones, that will decrease heart rate and decrease cardiac output. And that's all we have to think about for heart rate. All right, now let's move on to stroke volume. So stroke volume is written as end diastolic volume and end systolic volume, and we subtract them from each other. So end diastolic volume is the amount of blood that's left over in the left ventricle after we're done filling. So after diastole, after we're done filling, the amount of blood that's left over after diastole, after we're done filling the heart. And theoretically, hopefully, a majority of this blood should be shot out during systole, ventricular systole, and the amount of blood that actually gets shot out through the aorta will be stroke volume. Okay? And systolic volume is the amount of blood we have left over after systole. So after we have contracted the heart, so most of the blood has already been pushed out past the semilunar valve, and now we're thinking about the leftover. That remains. We're always going to have a little bit left over, but sometimes we might have too much, sometimes we might not have enough, and so we can have factors that affect end systolic volume. And I'd also like to point out that if the relationship between EDV and stroke volume are proportional. So if EDV increases, stroke volume will also increase. But if ESV increases, stroke volume will decrease. And a good way to think about this is with some math. So if EDV is 10 and ESV is 10, well, that's not representative. Let's say it's 9, then stroke volume equals 1. But if I increase EDV, and let's say that I change 10 to, 12, and I subtract 9, right? I'm going to increase 1 to 3. Okay, so stroke volume increases. Or I could decrease stroke volume, or end systolic volume, excuse me, and decrease it from 9 to, let's say, 6. Well, if let me increase that. Let me go from 9 to 11, and that will, let me start over. So EDV is directly proportional to stroke volume. ESV is inversely proportional to stroke volume. So let's say that I have 10 EDV, 5 ESV, right? Stroke volume then would be 5. But let's say I change EDV and I increase EDV to 15, right? Now I'm going to increase stroke volume, and that will be 10. Okay? But what if I went back, and I went back to 10, and let's say I change ESV and I increase ESV to 7. Well, now stroke volume will decrease, so it went from 5 to 3. So if it helps to think about it mathematically, I would do so. All right, so let's think about these one at a time. First, we're going to start with EDV, and I would encourage you to use a lot of colors when you're drawing this out. So first, EDV. EDV is primarily influenced by preload, and preload is the amount of blood and pressure that is built up right before we actually eject it out, so right before ejection fraction. And preload is affected by two things. One is venous return, so VR, and 2 is filling time. Okay, so let's think about this. If we're increasing venous return, so we're increasing the amount of blood that goes back to the heart, that will also increase end diastolic volume. And if we increase end diastolic volume, that will increase stroke volume. And if we increase stroke volume, that will increase cardiac output. If I decrease the amount of blood that's coming back into the right atrium, that will also decrease end diastolic volume, which decreases stroke volume, which decreases cardiac output, and therefore decreases blood pressure. All right, let's think about filling time. So if I increase the amount of time I have to actually fill, if I think about the amount of time that I have to actually fill the left ventricle, then theoretically I should get more blood in that area. So that will also increase EDV, increase stroke volume, and therefore increase cardiac output. If, however, I do the opposite and I actually end up decreasing filling time, well, that'll do the opposite effect. I will decrease end diastolic volume, decrease stroke volume, and also decrease cardiac output. Relatively straightforward. All right, so now let's take a look at this graph so we can represent this graphically. All right, so this dotted line is what normal stroke volume would look like, and stroke volume is the width of this curve. That's how it's represented. Okay, And I'd also like to remind you that this point right here, let me go into smaller font. This point right here is EDV. And this point right here is ESV. Okay, so the distance between the two, if we subtract the two, if we take this and subtract it from this, well, that equals stroke volume. Perfect. Okay, this line right here represents contractility, and we'll get to contractility. Okay, so if we're only changing either EDV or ESV, then everything else should stay the same. We should only be changing one thing at a time. All right, so let's go ahead and do that. Since this part of our table is just focusing on EDV, let's go ahead and change EDV. So let's look at what happens if we increase EDV. So if we increase EDV, we're going to shift to the right. So this point will be a little further out to the right. ESV stays the same. And our curve might look a little something like this. Okay, and now our stroke volume went from this to actually bigger stroke volume. So that increased our stroke volume by increasing EDV. And let's see if that's true with what we've already drawn out. Increase, 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 increase. Yep, that looks correct. So we're increasing cardiac output, we're increasing stroke volume. Perfect. All right, so now let's do the opposite. I'll go ahead and do that in blue. Okay, so instead of increasing EDV, let's decrease EDV. So instead of that point being here, we're going to move it a little bit more to the left, decrease. Everything else stays the same. Okay, and now my stroke volume has actually decreased from normal, so we're decreasing stroke volume. Okay, perfect. So that does represent what we're looking at. So this is an example of what preload would look like if we just changed EDV. Awesome. Okay, that's all that we have to think about for EDV. ESV is a little bit more complicated though. ESV is also affected by preload, so I'm going to write preload here as well. And preload again is venous return and filling time. So let's think about these one by one. If we increase venous return, preload. Preload is the amount of, we've already discussed preload, but preload is the amount of blood and pressure that is built up right before we actually eject it out of the heart. So if we increase the amount of blood that's there, such as increasing venous return, that will increase ESV, but if we're increasing ESV, that will actually decrease stroke volume because they're inversely related. And if we're decreasing stroke volume, that will also decrease cardiac output and then decrease blood pressure. Okay, the opposite will be true too. So if we're increasing venous return, we're increasing end systolic volume. That will, I drew the opposite arrow, excuse me. If we're decreasing, if we are decreasing venous return, we are decreasing end systolic volume. That will increase stroke volume, which will in turn increase cardiac output. All right, and filling time is exactly the same relationship, where if we increase the amount of filling time we have, that means we can end up with more blood in the heart. And if we're decreasing the amount of filling time we have, then we're decreasing the amount of blood that's left in the heart. Okay, so that's preload. I'm going to go ahead and erase, so we have enough room to talk about the next factor that affects ESV. And that is afterload. All right, so afterload is the amount of pressure and blood that is being forced upon the aortic semilunar valve. Okay, so we're trying to get blood past the aortic semilunar valve and into the systemic circuit. So we're thinking about the blood and pressure at that point. So how can we affect that? We can affect that with two ways, and that's with vasoconstriction and vasodilation. Okay, and now these two things are a little difficult to explain with afterload. So I'm really just going to primarily focus on how afterload affects cardiac output, and we're going to go one at a time. So afterload, if we increase afterload, okay, that'll directly increase end systolic volume, which in turn will decrease stroke volume, which will decrease cardiac output. And the opposite is true. If we decrease afterload, that will decrease end systolic volume, which will increase stroke volume and increase cardiac output. Awesome. So now let's represent that graphically here. Okay. And again, I want to remind you that here we have end diastolic volume, and here we have end systolic volume, and this is representing contractility, right? Okay. So afterload, in afterload, we are only changing end systolic volume, okay? So here, let's say that we are increasing end systolic volume. So that means our point is shifting a little bit to the right. Okay, and our curve is going to look like this. Perfect. So stroke volume went from all the way across, and it's actually shortened a little bit, so now stroke volume has decreased. All right, and let's do it the opposite way. All right, so if I've decreased afterload, so my end systolic volume has shifted a little bit to the left, but everything else has stayed the same. All right, my stroke volume has actually increased. All right, now let's make sure that that's correct. So end systolic volume, when that was increased, stroke volume decreased. When end systolic volume decreased, stroke volume increased. So let's make sure that that inverse proportion is what we calculated. So that's correct. So if we increase end systolic volume, that decreased end systolic volume, that decreased stroke volume. If we decreased end systolic volume, that increased stroke volume. All right, that looks good. Okay. Now the last one we want to talk about is contractility. Let me erase here so we have enough space. Okay, contractility. Okay, so contractility. Contractility is the ability of the heart to contract. And this is really important because this really represents how efficient the heart is at getting blood out. And the way we affect contractility is through what we call ionotropic factors. And ionotropic factors can either be positive, ionotropic factors, IF for short, or negative. Okay, and positive ionotropic factors does not necessarily mean that it is a good thing. Positive means that it's contributing, so we're adding to that. Negative means we're taking away from that. So in order to positively add to contractility, we're going to stimulate sympathetics. And sympathetics usually means we're releasing norepinephrine and epinephrine. All right? And when we're contributing positive factors, and we're contributing sympathetics, norepinephrine and epinephrine, that is actually going to increase our contractility. All right? Negative ionotropic factors are that would be activating our parasympathetic nervous system. And our parasympathetic nervous system is primarily releasing acetylcholine. And if we are increasing parasympathetics, we are actually decreasing contractility, all right? And you can think about it this way. Sympathetics, if we are increasing the ability of the heart to contract, in the short term, that'll be fine. In the long term, the heart really can't sustain that. And the inverse is also true for parasympathetics. Parasympathetics will be very vital in balancing out the sympathetics, but in the long term, we can't just have parasympathetics turned on. Otherwise, we won't be able to contract very well. So there's some sort of sweet spot between the two of them. Just in order to understand this chart, we're going to focus on them one at a time. Okay, so positive means we're adding to this, we're activating sympathetics, we're contracting harder, faster, I shouldn't say faster, but harder. We're contracting harder against the blood that we have pulled in the left ventricle. Okay, so if we're contracting better, I'm going to go back to red. If we're contracting better, right, then the amount of blood we have left over in systolic volume is actually going to be less. which makes sense because if we are contracting better, then stroke volume should be increased. And if stroke volume is increased, cardiac output is also increased and blood pressure is increased. Okay, so we are contracting better, we are contracting more, we are contracting more blood, so the amount of blood that would be left over as end systolic volume should be less, and end systolic volume is inversely proportional to stroke volume, and so stroke volume should be increasing. Okay, the inverse is also true. If we stimulate parasympathetics, that means contractility is going to go down, and if we aren't contracting as much, the amount of blood that is left over is more, and if we are increasing the amount of volume of blood we have left over, then that means the amount that's actually leaving is less, so stroke volume is less, which means cardiac output is less. Okay, let's represent this graphically. So, right here on our little chart, on our little graph, let's go with red. Oh, I want to remind you this is EDV, and this is ESV. Okay, and now we're not changing these are staying the same, right? What we are changing is contractility, which is the slope of this line. Okay, so if we are positively, I shouldn't say positively, but if we are increasing contractility, well, this dotted line should actually increase. The slope of that line should increase. So if we increase contractility, the slope of that line will increase. If we are decreasing contractility, then the slope of that line should decrease. Okay, so now let's represent what that looks like for stroke volume. So if we're increasing contractility, we have to make this regular curve somehow fit for this new line. So I'm going to follow end systolic volume up here, like so. Oh, I'm sorry. So if I'm increasing contractility, the amount of blood that I have left over after systole is going to be less because I'm contracting better, I'm contracting more, so the amount of blood I'm going to have is less. So I'm going to draw the beginning over here, shift my, and EDV should stay the same. So my line is going to look like this. This should come up and meet my new contractility line. I'm going to meet it over here. Put ejection fraction here. Boom. So now the amount of stroke volume has also increased. So stroke volume has increased. All right, let's make sure that's the same over here. So if I'm increasing contractility because I stimulated sympathetics, I'm increasing contractility. The amount of blood that's left over is much less. Stroke volume has increased. Okay, that's awesome. And then that will increase cardiac output. Okay, let's think about the opposite now. I'm decreasing contractility. All right, so I'm decreasing contractility. Okay, so my ESV is going to increase because I'm decreasing contractility. I'm not as good at moving blood out as I was previously. So ESV has increased. EDV stays the same. Okay, ejection fraction. So my stroke volume has now decreased. Perfect. That should be inverse of what my previous example was, so that sounds right. Contractility has decreased. Stroke volume has decreased. I'm not getting as much blood out during every contraction. Perfect. Contractility. Okay. Last but not least, now we got to think about total peripheral resistance. And total peripheral resistance is focused on just the arterioles, or the arteries. And total peripheral resistance is affected by three things. The first is blood viscosity. And being viscous means the amount of thickness we have in our blood, or how good is the fluid at moving through whatever space that it's trying to move through. And the main way we affect blood viscosity is with red blood vessels, or red blood cells, excuse me. Red blood cells. So if we increase the amount of red blood cells we have in our blood, in our red blood cells in our blood vessels, then it'll become more viscous, which will increase the amount of total peripheral resistance we have, which will in turn increase blood pressure. Okay, and the inverse is also true. If I decrease the amount of red blood cells I have, now I'm less viscous, and total peripheral resistance will also decrease. And what are ways that we can actually change how many red blood cells we have? Well, at the level of the kidney can respond to low O2 concentrations, and in turn release EPO, and EPO will go to the red bone marrow, and tell the red bone marrow to produce or use its stem cells and produce more erythrocytes or red blood cells. Perfect. Okay. The second thing that can affect total peripheral resistance is turbulence. So turbulence, just like you would experience on an airplane, is how bumpy the area is surrounding the blood and within the blood vessel. So if it has more surfaces or more uneven surfaces to bump up against, that will create really turbulent blood flow, and so it'll push against the lumen, the tunica intima of the blood vessel, and that will increase the amount of resistance you have. So turbulence could be prevalent in the chambers of the heart, for example, so the two atria or the two ventricles, because they are uneven surfaces. It could also really be present when there's a buildup of plaques. Plaques. So from lipid deposits or debris. So if you increase turbulence, that will increase total peripheral resistance, which will increase blood pressure. And if you decrease turbulence, that will also decrease total peripheral resistance. So if you don't have as many plaques, not as much resistance. If you have more plaques, more resistance. The final thing that contributes to total peripheral resistance is what we call vascular resistance. And vascular resistance is primarily factored by friction. So the frictional force that blood actually has to fight against in order to get through the blood vessel. And so two things contribute to friction: diameter and length of the blood vessel. All right, so now let's think about this. If I'm increasing the diameter, I am making the diameter from this to this, making it nice and big, but blood flow stays the same, the amount of red blood cells in it stays the same. Well, now I have more space for all of that blood to go through, and so the actual friction it causes is going to be less, which decreases the resistance it would cause. That would decrease. Oh, here, let me do that in another color. I apologize, so that's not confusing. Okay, if I increase the diameter, that will decrease the friction, decrease vascular resistance, which will decrease total peripheral resistance. Okay, the opposite could be true. If you think about decreasing the diameter, so we went from a really big to a really small, that really small diameter but the same amount of blood flowing through it, well, now we've increased the amount of friction that blood has to fight against, which increases vascular resistance, which increases total peripheral resistance, and therefore increasing blood pressure. Okay, length is a little trickier. Let's say this is a normal length. This is normal. If you extend the length, if I increase length, right, now I have more surface area for those red blood cells to bounce against. Well, that will increase the amount of friction I have to fight against, which will increase vascular resistance, and that'll increase total peripheral resistance, which will increase blood pressure. Or if I decrease the length, that's not very decreased, but if I decrease the length, well, now there's much less surface area for me to fight against. Let me do it in a different color. If I decrease the length, that's less friction I have to fight against. The resistance decreases, total peripheral resistance decreases, and blood pressure decreases. And that's it for all of the factors that affect mean arterial blood pressure. Mean arterial blood pressure can be calculated with diastolic blood pressure plus 1/3 times systolic blood pressure minus diastolic blood pressure. It can also be measured with pulse pressure. However, I won't really be using pulse pressure on the exam, so I'd be more familiar with this equation. And we can even do some math with this equation. And let's just take like average blood pressure. So if blood pressure is 120/80, let's see what mean arterial blood pressure would be. This blood pressure would probably be taken at the brachial artery or maybe the radial artery. So this is blood pressure at one instance, at one time, at one location in the body. Mean arterial blood pressure, mean, means we're taking an average. So we're taking the blood pressure that would be systemically contributing, and what would that number look like? So this is going to be a single number versus blood pressure at one location would be systolic over diastolic. Okay, so we can take these numbers. So diastolic is 80, 1/3 systolic is 20, diastolic is 80, 120 minus 80 is 40, times 1/3 is about 19, 80 plus 19 is about 96. Maybe my math is off, but it's close. All right, so mean arterial blood pressure 96, that seems reasonable. That should be somewhere in between the values of these two because it should be an average of the systolic blood pressure and the diastolic blood pressure. So the pressure that the heart has to fight against during every contraction versus the amount of pressure the heart has to fight against in order for it to fill again. Okay, and that's contributed by both total peripheral resistance and cardiac output. All right, I hope this video was helpful.